He's only one from here.
Yeah, I started signing coming out again for almost 10 years.
Chris, how are you today? Very well, yourself?
Never normally this way.
Were you sitting?
Steal that chair or what? Yeah, I take it.
Everyone can find their seats, please. Alright, everybody, I think we're ready to begin. Everybody's getting settled in. Excellent. Alright. Thanks, everybody, for showing up. Welcome again, my friends, to ASHRAE's January presentation. We've had a couple months off with Christmas. I trust that you all enjoyed your holidays, and we're right back into it now. So the first thing that I'll do is introduce the Board of Governors and the Executive. I think we have most of them here tonight. First is Richard Cameron with ProEng Consulting. Richard is here. There he is.
Waved already.
Right. Oh, okay. Sorry, I missed the wave. Chris Frawley, one of the governors. Chris Fudge is a governor. Aaron Dobson. Dan Redmond is not able to attend. We have Adam Graham, who's the secretary this year. Abby Saunders, our treasurer. There she is, good. George Mamari, the president-elect. Rod Potter is our past president. He's not here tonight. And my name is Steve Moons. I'm your president for this chapter year. So there's a few items on the business agenda to get through. The first thing we will start with is to have Adam Graham come up and introduce our guests and speak a little bit about the seminar that we have upcoming in the new year.
Hello. All right. Well, hello everyone. Welcome. First, I'll just go through the list of guests. We got a good number of guests out today. So we got Akil Al-Yacoubi from Algonquin, Stephen Leinke from Train, Luc Mantin from EI Solutions or Munters, Kevin Cheevers from HDS, Jean-Francois Brisson from HDS, Jennifer Van Galder from Algonquin, Evan Boucher from Long Hill, Ben Robinson from Dilfo, Alex Roy from Dilfo, Jacob Huff from Algonquin, and Ashley Lance from VRN. So thanks to all the guests for coming out, and thank you everyone who sponsored a student tonight. guess I'm back up.
Yes, you are.
So I'm just going to talk to you guys quickly about the upcoming seminar. So there's the part 2 of the pumping system seminar that we'll be doing on March 4th. So the date's been pushed back to March 4th now. But it's going to be more details on what the previous one was on different types of pumping, pumping systems, variable primary, primary secondary systems, go into heat exchanger selection types, performance. So it should be a very good, well-attended seminar. So you can go online probably within the next couple of days and register for that. So I encourage all of you to come out and let me know if there's any questions. Thank you.
Thanks, Adam. Next, we'll have Adam Moons come up. He is the chair of our membership committee, and he will introduce this month's new members.
Thanks, Steve. Just 2 new members to introduce this year for the start of the year. Mr. Peter McClure and Mr. Rod Sproles. That is all.
Very good. Very good. All right. Next, George Mamari will come up. He is the chair of the Research Promotion Committee. That's something that he's taken on with a lot of verve this year. We've had a lot of success to date. He'll give you more of the details, but pay close attention. This is a really big part of what we try to accomplish as a chapter.
All right, hello everybody. Welcome to the January Research Promotion Night. As all of you might already know, ASHRAE Research is a very, very large part of what we do every year. It's a big component, and it is involved, a lot of effort is involved into raising these funds. So as most of you know, year after year we come knocking down your door asking for some money. And most of you get accustomed to the phone calls, you get accustomed to the raffles that we do at the monthly meetings, as well as the special events that we organize to help collect these funds. But they all have a purpose. And a lot of the purpose itself is clearly identified, in my opinion, in the ASHRAE mission and vision statement, which I'm going to read out loud. So ASHRAE's mission statement is to advance the art and science of heating, ventilation, air conditioning, and refrigerating to serve humanity and promote a sustainable world. ASHRAE's vision statement is ASHRAE will be the global leader to
What you do?
I don't know. You guys can hear me though?
Yeah.
All right. So the vision statement, ASHRAE will be the global leader, the foremost source of technical and educational information, and the primary provider of opportunity for professional growth in the arts and science of heating, ventilation, air conditioning, and refrigerating. The key words here are advancing the arts and science and being the global leader. And most of you will probably agree with me that ASHRAE currently is the global leader in both in the HVAC industry. If ASHRAE funding ceased to exist, obtaining those 2 keywords wouldn't be possible. So every year ASHRAE funds hundreds of projects, each serving a purpose of either updating outdated information or providing new information in areas of interest. In this slide that's going to be looping throughout dinner, I've listed the projects that are currently undergoing in our region. Just to name a few, we've got performance of pressurized stairwells with open doors. We've got updating the climatic design data in Chapter 14 of the 2017 handbook. And there's also a study on an advanced hybrid air filtration system. And the list goes on and on. There's quite a few projects going on. So try to remember that a large part of our industry and even our careers have all evolved due to entities such as ASHRAE who keep pushing to advance the science and the art of HVAC. Try to remember this when we're calling you in the next couple of weeks with our calling campaign to ask for your donation. So thank you in advance, and hope to hear from you soon. Thanks.
That's excellent. One thing I would mention as well, George, as you mentioned, is doing raffles. We do that every month. This month, we're raffling off 4 tickets to a Sens Carolina game on February the 16th, donated this month by Airtron. We've had a number of suppliers and contractors donate tickets throughout the year. We'll continue that process. If you haven't gotten anything from George, he's still at the back, happy to take your money and give you an excellent chance to win some tickets. And it's stuff like this that does go a long way towards making our goal. So if you have a couple dollars to spare tonight, George is at the back. He's happy to come see you and get you some of those tickets. Tonight we have 3 tabletop presentations to my left on the far side of the screen. First, I would ask for Luc Martin to come up with Munter's Group and to give a brief rundown of his tabletop.
Hi, Luc Martin from EI Solution. We rep Montreal commercial product to Canada. I'm working for the Quebec province and I'm covering the Ottawa market. We mainly work in the rink business where we have a low dew point to achieve. But tonight I think the presentation is in Chill Bean, and we did one project in Ottawa. I think it's a police station. We can lower the dew point really low, so you can achieve you can only use the minimum air by the coal to make your Chill Bean project. Thank you.
Great, thanks. So once the presentation is over, feel free to talk to any of the guys on more information to a particular product. The next tabletop we have is Train, and I'll have Andrew Klassen come up and speak to their product.
How's it going, everybody? I'm Andrew from Train. Today we have BKM, and we can achieve up to 90% efficiency in winter months for energy recovery. Happy to come and see me at the paper location. Thanks.
And lastly, we have Total HVAC here presenting Aon and Semco. So if Andrew Duma can come up.
So as Steve mentioned, we're representing 2 manufacturers today. One is Aon with their packaged energy recovery wheels. They've been doing this technology for 20 years or so it's very proven technology. Also we're presenting Semco, who also make energy recovery wheels, and if you want to see how 2 wheels can save you more energy than one, come by and see us after the presentation. Thanks.
That's it for the business session. We'll adjourn for dinner, and afterwards we'll get going on the evening session. So enjoy your dinner.
I don't know about the problem. The goodness. For the kids there, the kids I have to say,
We do though, we have to draw the tickets, draw the raffle tickets for the Sens game. George's incessant pestering of you was able to raise $470 tonight. So that's an excellent result. Thanks very much to everybody who donated. And again, big thanks to ASHRAE for donating the tickets and the parking pass. So I'll get Paul to make the draw. All right, and the winner is ticket 793514. 514. Hey.
What a coincidence. What are Andrew doing from Total HVAC?
Thank you very much.
Good job.
All right, so this evening's presentation, we have Paul Piper in town. Oh, actually, before I get going, I should mention that coffee is available to anybody just at the back, so if you want some, serve yourself. And also, we have a pretty good number tonight, so I know we've had to spread to the far sides of the tables. If you wanted to bunch it a little bit, if some people aren't able to stay for the evening presentation, you want a better look at the screen, and you don't have a good angle for it, just draw your chair around to the back, make sure you can see what you need to. But I'll introduce tonight's speaker, Paul Piper with Benmar CES Unitary Products. Paul is educated in Montreal and works there now. He's been in a number of different industry positions. Currently, like I said, with Benmar. And we're speaking tonight on air-to-air energy recovery. So he'll go through a variety of energy recovery methods, and feel free to, he'll stick around afterwards if you have any questions, or as long as you're going to take. So without further ado, ladies and gentlemen, Paul Piper.
All right. Okay, so can everybody hear me all right in the back? Yeah, it's all good. All right. Okay, so yeah, my name is Paul Piper. I work for Benmar CS. I'm the product line general manager. Ignore most of that, but just know that I'm pretty involved on the dark side of ASHRAE. So mostly on the national level, I'm involved in TC55, which is area energy recovery, TC812, which is desiccated equipment and components. If you find yourself in Chicago or just interested in the technologies, we're always looking for new members, so feel free to come out. Also involved with ASHRAE as well, so you'll hear me talk a little bit about that tonight. And most of my experience has been on the manufacturing side, so I'm going to be talking about energy recovery. I'm going to talk about the technologies, in particular the metrics, and how to measure them, and how to actually get them into the box. And we're going to talk a little bit about some controls and some other little odds and ends relating to energy recovery. So those are the learning objectives. So I'm going to start at the beginning. I'm going to start off a little bit with the standards. It's not quite as boring as you think, but I just want to talk a little bit about some of the standards, because that goes into the metrics for when we're measuring those metrics. Also mention, I'll usually keep this event to a tight 45 minutes. So if you do want any questions, though, feel free to raise your hand. I'll field any questions in between, or if you want to ask them at the end, or just pull me aside if you're shy, feel free to do that as well. But going back to the standards, actually let me do one thing real quick. I'm assuming we have a lot of manufacturers representatives here. Do we have a lot of consultants as well? Consultants? Contractors? All right. Okay. So the presentation is fairly balanced, but if you have some specific practice, I try to make it as practical as possible as well. If you have specific questions, feel free. I'll try to cover that. But again, I'm trying to get into the metrics. So talk about the metrics. I want to go back to some of the standards, what we measure and why we measure them. So when we talk about energy recovery, one of the key areas that we talk about in 62.1 is under the classifications of errors. So 516.1, that's correct. We talk about, when we get into that section, 516.1 and the classifications of error, there's a bunch of different classes of error. I believe everybody's mostly familiar with them. Class 1, which is relatively benign, like a space like this. Class 2, which may have some unpleasant odors, let's say like toilet exhaust. Class 3 is typically a little bit more, it's a level above that if we talk about beauty salons, or if we talk about even parking garages where you have not just an odor present, but also something that will irritate your upper respiratory area. And then finally class 4, which you're not allowed to mix with anything. You have to keep that entirely separate. We talk about those classes of air. Anytime you mix a higher class of air with a lower class of air, you need to redesignate, and that's section 516.2. Under that redesignation, if you're using air-to-air energy recovery in your equipment, there's an exception. And that exception allows for you to mix class 2 air with class 1 air up to 10%, and class 3 air with class 1 air up to 5%. So you're allowed a certain amount of recirculation, you're allowed a certain amount of mixture. Cross-contamination is a term. There's a very specific term used by ASHRAE now called exhaust air transfer ratio. I'll explain what that means to you. But when we talk about exhaust air transfer ratio, The reason we talk about it is because it ties back to 62.1. So when you're bringing that outside air dilution into the space, you want to maintain the amount of, the correct amount of fresh air. You want to make sure that you're adhering to the redesignation law. So again, 10% Class 2 to Class 1, 5% Class 3 with Class 1. And under any circumstances, you're not allowed to make Class 4 with any type of air. As I talk about the different types of technologies, the leakage that's present in each of the technologies, as well as within the cabinet, you're going to need to adhere to this, and something will need to be done, whether using a plate, whether using a heat pipe, or whether you're using an enthalpy wheel. All applicable, all technologies, certainly all technologies, once you put them into a cabinet, are affected by some manner of leakage. So it's a consideration depending on your application. The other standard, key standard, we can talk about a lot of standards, but the other key one relating to energy recovery is 90.1. Going back to the beginning, we talked about 90.1 2007. It's not the first instance of energy recovery, but it's the last instance where a single rating point was used in 90.1 2007. In it, when you use energy recovery, 6.5.6.1, that's the subsection, we talk about using energy recovery. You're allowed, anytime you introduce energy recovery, you're mandated to use energy recovery in any system that 80% or more outside air within the space. So that energy recovery device needs to be 5,000 CFM or more, 80% or more outside air, and of that, you need to have a performance metric of maintaining 50% recovery effectiveness. The term effectiveness in 90.1 is not your typical ASHRAE definition of effectiveness. I'll come back to that in a second. But this is a typical arrangement. You can see an enthalpy wheel here, only because it's easier to draw, but it applies. You have a variety of different stations. Your outside air, your X1, and X1 being representing, it could be temperature, it could be humidity, it could be total energy or enthalpy. But typically X1 is your supply air entering in this grid over here. X2 is your supply air leaving, or your supply air to the space. Supply air entering would be your outside air, or simplified. X3 is your exhaust air entering, typically your return air. And X4 is your exhaust air leaving, typically what you would exhaust into the space. So when we look at that, any energy or any effectiveness definition is ultimately the actual amount of energy that you recover. So how much energy do I recover is your formulation. So the difference between X2 and X1 over what is the maximum possible amount of energy that I can recover. And that difference is your return air, X3, and your outside air, X2. Any effectiveness, that's ultimately what the definition is. When we talk about 90.1 and under 90.1, what we're talking about is this right over here. So you have X2 minus X1 over X1 minus X3. The differences that we see with a traditional effectiveness is over here. Oops, is over here on your traditional effectiveness. In which case you're allowing for your mass flow rate, in this case represented by CS. Simplified at standard temperature and pressure, you're looking at typically 1.08 times your delta T, so on and so forth, over your minimum airflow, again, times that X1 minus X3. Minimum, again, how much energy can I possibly recover? My outside air, less my return air, times the minimum amount of volumetric flow, which gives me the total amount of BTUs that I can have. That's ultimately what you look at when you're looking at effectiveness. When we talk about 90.1, the only thing you need to do in order to meet that requirement is your effectiveness needs to be 50, and that is your difference strictly just in your temperature or humidity between the two airstreams in order to meet that performance. Assumes balanced flow, which is certainly not always the case, because there's no mass flow rate. So a much more simplified term, the newer version of 90.1 will have a clarification. It will no longer call that effectiveness because it's actually very confusing, and I have to waste time on a slide like this constantly. But the other thing that I would call your attention to is the AHRI, and actually the new version of the handbook also has this designation, and it introduces a term called your EATR, your exhaust air transfer ratio. That's that cross-contamination, that carryover, and it looks a little bit more complicated. Ultimately, it's the same definition, but what actually is expressed here is we're eliminating the amount of exhaust air that finds its way into the supply air without ever having passed through the heat exchanger. So it gives you a net true effectiveness that you wouldn't normally pick up if you were only measuring temperatures at each one of those stations. So that's the long story for that. 2010, the 2010 version of 90.1 introduced, rather than just that one rating point of 5,000 CFM and 80% outside air, went to more of a regionalized approach, which is what we see in a lot of the other standards. And that regional approach refers to a particular table and varies depending where you are in North America. In this case, I have obviously the American map. We're in that white space up above, as you all know. So actually, I have another presentation. I have all the dots actually, painfully mapped out all the dots. We're mostly 7 and 8, basically, going out there. And the back of 90.1 has a list. I have that list. I actually have a really pretty slide we've spent a lot of time on that actually has the Canadian portion of this map, which I neglected to introduce, so I apologize for that. But anyway, we're up in that 7-8 category up there. Some regions are 6 in Montreal from where I'm from. And the table is represented as follows. So rather than that one rating point, 5,000 CFM, 80% outside air, which is ultimately that position right over there. Now we have a variety of different outside air flow rates that range anywhere from 100% or greater than 80% down to as little as 30% outside air. So based on that, what was done actually in 90.1 in the mechanical subcommittee was energy recovery was modeled in a very similar way to the advanced energy design guides. If you're familiar with the methodology for that, you had a variety of different buildings that were modeled in each of the different key climate zones, and energy recovery followed that same type of model, and based on varying outside airflow rates and different volumes of air, where and when energy recovery was the most cost effective found its way into this table. So even if the local standards, or if you're reviewing a project and you're not modeling, this table, or the newer version of the table, which is a little bit even more accurate, is actually a pretty good cheat sheet to say, okay, I'm looking at this building, I have X number of systems of such and such CFM with this percentage of outside air. You can quickly refer to this table to see if you even want to consider using energy recovery for your application. So it's very useful on that standpoint. But the bottom line is we're seeing a lot more energy recovery used in a lot of different areas. So ultimately, where we see the original rating, where there's no changes, is these areas up here at the top. And I'm just going to try to, usually I'm a little bit off center. So the key one that we want to look at really is the bottom line. So the bottom line, whereas previously in more Canadian climates, 7 and 8, and a little bit of 6, we're looking at 5,000 CFM, and now at 80%, anything more than any system needs some form of energy recovery. And then when we look at some of the systems that are maybe 30% outside air, which is not outside the realm for rooftops, when we look at that, any system over 2,500 CFM needs some form of energy recovery, which is why you see a lot of the chiplet manufacturers and a lot of the standard rooftops incorporating energy recovery in order to be compliant with these standards. The 2013 version gets a little bit, yes?
But this is not a mandatory requirement, right? It's a prescriptive requirement.
This is following the prescriptive path, correct, exactly. Following the prescriptive path, what we find, a lot of the questions that I get is when people are starting to model systems, there's a lot of exceptions, and there's a different part there's a different presentation I do just on the standards that goes over the exceptions, but when people start modeling them, more and more often they wind up using energy recovery in areas even where it's not mandated. But some of the questions that I used to get before the table from places like hot and humid climates, right? Florida, South Carolina, North Carolina, they're saying, I want to use energy recovery on my project, but I have to follow the prescriptive path. I have to have the minimum. Can you give me anything that I can justify using energy recovery? Now we actually have this table. So this is the minimum path. If you look at other areas and you try to squeeze out as much energy recovery as you can, certainly there's areas in the exceptions where we're looking at laboratory exhaust. There's a lot of specialty applications, kitchen hoods, commercial kitchens where people are using energy recovery that previously do not require energy recovery. In the 2013 version of the standard, we refined the table. We're using the royal we. I didn't have anything to do with the table. I was an observer. But the committee, the 9.1 mechanical subcommittee, you'll find the calculations even more to consider systems with both continuous and non-continuous ventilation. Those were defined as anything more. Continuous ventilation was anything more than 8,000 hours per year, and non-continuous ventilation was anything less than 8,000 hours per year. So that single table was now updated to have two tables, 6.5.6.1-1 and -2. And these tables, there's actually two changes to 2013, which I don't want to gloss over. One is, again, we have the two, and if you look at the zones that we have on the side, there's not an exact correlation between the top and the bottom, but if we look at 7 and 8, we look at non-continuous ventilation up at the top, or sorry, continuous ventilation, at the bottom, any system in a northern climate. So if you have an application that's 24/7, operating most of the week, you're going to need some form of energy recovery to make sense. When we look at non-continuous ventilation, there's a slight bump in the 7 and 8. So it's not quite, we're looking at 2,500 CFM, basically unchanged. But the difference that we see over here is the table has now been expanded to go down to as little as 10% outside air. So 10% outside air is not a lot of air. That affects a lot of systems. And when we look at employing energy recovery and incorporating energy recovery, it's fine and dandy when we talk about 100% outside air, we talk about standalone units and we're packaging them together and putting it together. But when you're trying to incorporate this into a single box and you're trying to design a system that accounts for 10,000 CFM and 1,000 CFM, because of the same fan system, it can get very complicated when you're looking at thrust control strategies, when you're looking at economizer in the shoulder seasons. Being able to design for that differential and having an efficient fan selection and just an overall decent design without looking at 3 or 4 fans can be a challenge. So I'll talk a little bit to that moving forward. When we talk about, again, areas 7 and 8, no changes, unless you go to continuous ventilation, in which case you require energy recovery. So that was a specific slide, so I'll scooch over those real quick. One thing I will talk about, though, as well, 189.1, which is your 90.1 is your minimum energy standard. 189.1 is your minimum high performance standard. So what's the least you have to do to have a high performance building? That's 189.1. The table that you see published in here has not been updated. It corresponds very closely to the 90.1 2010 version of the standard. It only goes down, it does go down to 10% outside air, but the continuous versus non-continuous has not found its way. It's a little bit out of cycle with the 2010 version, but the next version of 189 should mimic that and potentially bump up or drop some of the requirements, because 189 is not necessarily driven by cost effectiveness as 90.1 is. They're driven by high performance. So you want a high performance space, you want a well ventilated space, you want an energy efficient space. So they may adjust some of the tables, most likely downwards, to incorporate energy recovery into a couple of areas. One thing that does change, that I call out, is rather than 50%, we're talking about 60% effectiveness. And if you're trying to squeeze out a little bit more recovery out of your system, if you look to that minimum of 60%, you try to squeeze out a little bit more, you're going to do better on your overall analysis for your energy savings. What does that look like when we're at 60%? Again, the same expression, 60% outside air. If I take a standard ASHRAE outside air summer condition, which is 95-78, and we plot it out, and we have a return air, in this case is 75-50%. Ultimately, what I'm doing, and maybe the visual wasn't there for the first one, was talking about the 50%, but ultimately what I'm doing is I'm drawing a line versus the enthalpy. So I'm looking at that outside air condition, I have my enthalpy point over here. For 90.1, halfway through is the target that I have to meet, which ultimately means any energy recovery device I have needs to hit that line one way or another in order to comply with 90.1. 50%, halfway through for 90.1, 60% in this case for 189.1. So the device, when we look at areas with high latent loads, typically we're looking at a latent device in order to get to that. Or in your conditions where our return air and our outside air are a little bit closer together, a little bit more westerly, hot and dry climates, for example, often you can get by with sensible devices that do the same thing. But ultimately, as long as you can hit that line, however you want to do it, That ultimately means compliance, and it can be achieved with both sensible and latent devices. 84 ultimately is your base program, is your basic standard for testing air-to-air energy recovery devices. A lot of the key manufacturers have been involved on the TC level in developing the standard because it's the baseline for ASHRAE 1060, which is the ratings program for the commercial devices that I'll be talking about very shortly. One thing I do want to mention is it's not a ratings program. You can't certify to 84. 84 tells you how to set up your lab, how to calibrate your devices, how to report your results, how to calculate uncertainty, the temperature differences. It has all the baselines, and it covers all of the different technologies that are available. ASHRAE is a subset of that. It's a ratings program operated by ASHRAE that takes the data in 84 and uses that to develop their certification program. So if you're looking for the program, ultimately this is it. The reason why I bring up ASHRAE is for that certification, but also because of the terms that are defined, that were defined originally in 1060. And these are the ones that I've already said, maybe once or twice. But that cross-contamination, that carryover, or in this case, the exhaust air transfer ratio. And as I said before, the exhaust air transfer ratio is the amount of exhaust air, on the right spot, the amount of exhaust air, and I apologize, I've inverted the stations with this little drawing, but the amount of exhaust air that actually leaks its way into the supply air without ever going through the exchanger. When we do that in the lab, your exhaust air transfer, ultimately what's done is we inject a tracer gas into the exhaust airstream. Usually it's SF6, sulfur hexafluoride. We take an ambient level measurement to get a baseline, and then we measure the supply airstream to see what concentration, what volume of that contaminant finds its way into the supply airstream. We can find out from that how much exhaust air is transferred. If we talk about doing this in the field, if you need to measure airflow as a contractor, you can use some other less carcinogenic and harmful tracer gas, but you can use carbon dioxide as well as some other gases as well. So it can be done in the field, same measurement, you inject it, you inject a certain concentration in return, you measure the supply, and you take the measurement, simple as that. The other thing that's important when we talk about cost, we talk about how to employ energy recovery. And depending on the application that you have and the differential pressures, you want to know what your outdoor air correction factor is. And your outdoor air correction factor is the amount of additional outside air, the amount of outside air, in this case fresh air, additional outside air you need in order to get the amount of dilution air that you calculate into the space. So in this example over here, it might be a little bit small to read in the back, but I'll provide a copy of the presentation to post to the website as well, so you can host that as well. But if you can't see it, what we have is we have a system that's about 5,000 CFM, and again, this is a wheel, but it could represent any technology. Any technology has a certain amount of OACF and ATL, depending on the design and differential pressures. But in this case, if I want to deliver 5,000 CFM into the space, in this case, I have an OACF of 1.08, which means I have an additional 8%. So I need an additional 400 CFM at this station in order to deliver the amount of dilution air that I have into the space. So if you have trouble in the field balancing units, if you're not getting air into the space with some type of energy recovery, make sure that it's sized correctly. Work sized correctly, measure the airflows, and see what you have on the ins and outs, because you may be, if it's a slightly different differential pressure, then maybe that was specified, because that never happens. But if you have differential pressures on the return air and the supply air, you might get more unanticipated leakage depending on the device. And then ultimately, where that comes into cost is ultimately where you have your fan placement. So if I have this type of arrangement, and I have my fan on my outside air position here, and I have a blow-through type of arrangement, now I have to upsize any preheat that I have, any filters, any dampers, as well as the motors and the power draw that I have on that, and then that air goes to my exhaust airstream, in which case I have to do the same to the exhaust with respect to the motors and the fans. So I have to account for that one way or another. There's a couple different arrangements. Most unitary standard product will bypass some of the concern because they're all pre-designed, basically pre-engineered. And most of these technologies are based around a draw-through type arrangement. Doesn't give you the shortest, most compact unit, but most of the unitary product follows this because it gives you the least amount of differential pressure between the two airstreams. In this case, both of my fans are operating at negative, so I have a very slight negative over here, I have a slight negative over here. If I wanted to figure it out, let's say I have, I'm at ambient, I go through a hood, I go through a damper, I go through a filter, I go through my heat exchanger, I'm looking at about maybe an inch and a bit, something like that. If I'm on a return air, I have a certain percentage of my external static pressure that I need to accommodate for. Maybe it's half an inch, maybe it's a quarter, 3/4 of an inch, and then I measure that. So I'm only looking at maybe about a half inch, maybe 3/4 of an inch differential pressure between the airstreams. I'm not going to get a lot of leakage, no matter what technology I'm going to use. So usually this is what's done, and it's usually accounted for in standard designs. But where you start to get a little bit more custom, semi-custom, if you have, if you're laying out an air handler, let's say example, a lot of consultants in this room, people in this room have access to air handling layouts from certain manufacturers. When you place your fans in that arrangement around the device, you want to make sure that you're accounting for that. Otherwise, you could be designing things that are maybe unintentionally a little bit too expensive. In this case, if you're doing a blow-through, draw-through, what I'm doing in this case is maximizing the amount of outside air correction factor. Now, the thing is, outdoor air correction factor and EATR are not directly related, but they, like it's not a linear relationship, but in general, the higher your OACF, the higher the outdoor air correction factor, the lower your EATR. Where this comes into effect is when we talk about the classes of air. I have that 5 and 10% that I'm trying to meet. When I'm arranging my unit, if I'm not getting to my 5 and 10%, you need to start playing with your design. You need to start either adding differential pressure, adding some dampers, playing with your fan assembly potentially, if you're trying to get to very, very low arrangements. So in this case, what you'll have is you'll have very low exhaust air transfer ratio, which is good if you're concerned about contaminants into the space. It's also good if you're concerned about sound, because your fan, your discharge sound power levels, because your fan is located very high up the stream. It's good also from a footprint perspective, so you have a very tight mechanical room. There's a lot of reasons why you'd want to go blow through, draw through, but make sure you're doing it for the right reasons, because you're also introducing higher amounts of outside air by doing this. So you have higher, where the example was 8%, you could get 10, 15% additional outside air into the space. A lot of air handling manufacturers and products have, SMAC Class 3 requirements of less than half an inch of leakage at 1.5 times operating or something like that. We're talking about very low amounts of outside air, but when we're talking about these types of arrangements, we're talking about 2%, 3%, 5, 10%. That's a lot of additional air. Maybe not so much on a small unit, and if we're doing draw-through, we're not really talking about much for unitary. But when we start talking about larger air handling units, we start talking about 20, 50,000 CFM type systems, that can add up and can have an impact on cost. So ultimately, we're trying to put the exchanger, yes?
Does that come from operational cost perspective? This configuration wouldn't increase your fan horsepower?
It would increase, yeah, in this case, because you have an additional, let's call it 10% additional outside air on this fan, but you'll also have 10% additional outside air on that fan as well. If you have preheat, you're going to have to upsize your preheat for the number of kilowatts as well. So it will have an operational impact, and I do a short course where I go over different configurations and I look at the annual operating costs. Because from a peak efficiency perspective, if you look at your combined efficiency, which I have here, my combined efficiency of that system is going to be much better than the average system. So peak efficiency is very good, but it doesn't tell the whole story. You really want to look at that whole system over the course of the year. And depending, I look at a few configurations in the other presentation where I look at a latent device. I look at, in this case, a wheel versus a heat pipe. So in a hot and humid climate where I have a high latent load, even with the additional outside air, that amount of energy that's available to me, I more than make up for it. But once I shift over into a hot and dry climate, that heat pipe now actually performs better, even though, because there's not as much latent to capture, so I don't need the latent. But I also have next to no leakage in the airstream, so I don't have the energy penalty. But it's not to say that wheels are better than heat pipes or vice versa. It is more to say of you really actually have to understand your application, what you're trying to achieve, and what's available to make the best decision for your project. So every technology is good as long as you understand how it applies into the application that you have. So when we look at the systems and we look at the combined efficiency, so if you're familiar with the EER, I'm sure everybody here is familiar with the EER, how much cooling do I deliver versus how much power do I consume? If you want a COP, it's basically dimensionless, but ultimately think of it in those terms. How much cooling versus how much power consumed. When we look at the EER of an individual, in this case, a weatherman, I'm kind of looking at the screen and I'm leaning off to the side. But ultimately, if I look at my packaged equipment that has an EER, my standalone device, my equipment, has what we call an RER. So my device has an RER which is expressed in the exact same terms. So it's in the same units as well. So it's in BTU per watt hour. And my RER is how much energy do I save, or how much cooling energy do I deliver with my device, versus how much power do I consume, including the parasitic losses of the static pressure through that device. So they're expressed in the same terms, but the reason why this was developed by ASHRAE is because if you take a standard EER and you apply it to 100% outside air energy recovery device, unitary or otherwise, your numbers are not going to shake out. I'm saving energy, but when we look at how much cooling do I deliver versus how much power do I consume, because I have introduced an energy recovery device into that mix, now the amount of cooling in my numerator drops because I have less tonnage, where I needed 20 tons before, now I only need 15. And I've also introduced an additional fan, which consumes energy, and I've also introduced a pressure drop, which also consumes energy. So based on those two, now my denominator is higher, my numerator is lower, so my EER, if I just follow through, is actually lower, but intuitively that doesn't make any sense because I'm actually saving energy. So this metric has the net cooling delivered, called the CEF. So it takes the cooling capacity of the device. So you can think of it as a built-up system, as it's shown here, or integrated into a single box with energy recovery as well as mechanical cooling. But ultimately, if you look at the mechanical cooling delivered, I look at the cooling delivered by the energy recovery component over the total power consumed. What I have is a combined efficiency, or CEF, which is a good way to rate the peak performance of a device. And you can think of it almost as an application EER. And for modeling systems, which is tricky with energy recovery, most of these standard modeling packages don't really model energy recovery well. But if you take your EER and you plug in your CEF as an application EER instead, you'll get a much better idea of modeling. Now, it's no excuse for, or not an excuse, but it's you can model it 365, and I've worked with consultants where I've run through, I don't know how many selections and performances and developed actual specific curves for a project to model it to nth degree of detail. But ultimately, if you want to use a standard modeling program, you can plug in your CEF into where you would plug in your EER for your component and get a reasonable number for how much energy is saved. TC55 is actually has an RTAR for research in order to develop algorithms that can be used by energy modeling programs to better characterize and capture energy recovery, not just the raw devices, sensible and latent, but also capturing that data during off-peak hours and allowing for economizing and cross-control. You basically have a TLL that you can call from in order to use that in place. So, energy recovery, the landscape, I've talked a little bit about. Now my life is mostly involved, at least for the next 6 to 8 to 12 months, is involved in standard unitary packages. So standard unitary ERVs, smaller units, typically under 15,000 CFM, maybe under 10,000 CFM. We also have semi-custom modular units, which is when we talk about these fan arrangements, and you're able to build these up with programs that the manufacturers give out to everybody. That's where you have to start to be a little bit more careful. And then we also have custom energy recovery, where you're going to want to rely on your supplier, your manufacturer, your representative, whoever that is, to guide you towards the right solution. But knowing some of these questions to ask will help you work with your partner to get to the right solution and get the right energy recovery design, if indeed that's what you need. So, ASHRAE Guideline W, in addition to the Advanced Energy Design Guides, I know we might have some students here still, but the Advanced Energy Design Guides from ASHRAE, if you haven't downloaded them, they're free to download. I would highly recommend it, very, very useful, covers schools, healthcare, buildings. I would also recommend downloading Guideline W from ASHRAE, which is also free to download as well. And it provides a lot of guidance on a lot of different areas for sizing and selecting package energy recovery equipment. It talks about these definitions that I'm going over, but it also talks about frost control and economizer and a variety of different areas that I won't be able to spend as much time in today. Very, very good reference. Classifies these different systems. So we talk about integrated systems, integrated air handling, as well as see, you got the weather in there. Integrated air handling over here versus the packaged systems. Ultimately, it's in the same box. The metrics still work when we talk about the cooling and all of that. It's packaged in one system, single footprint, typically a nice little cube. We talk about standalone systems. There's a few different ways you can look at standalone systems. One is your typical standalone system. So your typical standalone system where you have separate ductwork feeding into the space, you have your rooftop. This is a very inexpensive, cost-effective way of doing things. You're using your chiclet rooftop, you're using a standalone ERV, you're building it up. Where you're going to spend your money is on ductwork, on labor, on installation, on controls to make sure everything works together, and on balancing. So if you're trying to make sure that your, certainly your first cost is going to be lowest, but you might have incremental cost after that. Then we also have standalone coupled, in which case you again have these two same pieces of equipment, but you're feeding one into the other. So that's one of the ductwork. This one right over here. So this one over here, you have your ERV that's actually feeding into the supply, into the space, and it's getting mixed in the ductwork. So imagine dampering in each one of those little places as well to make sure that you get the right balance as well. So very cost effective. You can also have unitized systems, which are pretty good for retrofit. It's a nice concept for retrofit. It looks like that, if you're not familiar. Basically built up, so you have a little system that sits on a sleeper curb and it's ducted directly into an existing rooftop. So it's a nice way to get some free energy if you're trying to recondition a unit that's been out there for a little while. One thing to consider though is with a lot of the new economizer requirements as well, you need to make sure you account for that. So again, tightly integrated controls, you want to be very careful on those. But a good economical way for retrofit. It's not always easy because energy recovery does require supply and exhaust airstreams to be side by side. So frost control. When we talk about different methods of frost control, there's a variety. When we talk about unitary product, typically we're looking at exhaust only or recirculation as methods of bypassing a device. You can see over here when we talk about different methodologies, if we talk about a static device, you have no choice but to go around. So one of the either exhaust only or recirc, you're dampering in order to be able to do that. Conserve double duty in our climate by being able to use it for economizer as well, so you can go from zero minimum outside air to 100%. So beneficial. You could also look at preheat, which will be applicable to sensible devices, plates and heat pipes, as well as wheels, in which case you can put preheat on the outside air to prevent condensation. Frost control. If you're not aware of the conditions for frost control, very, very simple. You need condensation on the exhaust airstream because counterintuitively, frost will occur on the exhaust, not on the outside air. And then when I was just starting off, I always thought that frost would be on the outside air, but really it's where the condensation occurs because ultimately you need water and sub-zero temperatures in order for frosting to occur. So you need that condition. In order to avoid that condensation, you're going to modulate your performance in the case of an activated device, an active device. So in the case of a wheel, you would be varying the speed of your VFD, the rate at which it transfers. If you have a runaround loop, you would vary the flow of the fluid within the circuit. And if you have a static device, you can't modulate the performance through the device, you need to bypass around it. Or you can look at full performance, maintaining full performance on your device and preheating upstream. I get that question a lot because we're trying to save energy with energy recovery devices. Do I need to use preheat? Does it make sense? Am I just throwing money back into it? Obviously, it's going to depend on the cost of energy to preheat, whether you use electric or gas or water, a boiler. But ultimately, in colder climates, when we look at extreme climates, when we look at one of the factors I work at is in Saskatoon, Saskatchewan. The outdoor air design is minus 40 degrees Fahrenheit or Celsius, same at minus 40. At that condition, if I was doing bypass, I would ultimately be bypassing nearly all of my air around that device. If I was modulating the heat wheel, it would be modulated to next to zero and basically be stopping. At those conditions, preheat is the only way really to handle that. However, when you're looking at a latent device, there is an argument to be made, so you may want to look at an analysis for that, of looking at a preheat performance versus limiting performance, because what you have with a latent device is you have all that extra latent energy. Operating at 100% latent energy and just bumping it off of the sat line, you can actually save more year-round versus modulating performance, either through bypass, where you're going to be bypassing a significant amount outside your limiting performance, or through some type of VFD where you're going to dial it down to almost nothing and have to make it up downstream. So there is a benefit. You may want to look at it. There are some cases, certainly in more northern climates, with latent devices where preheat is probably the best way to go. System balancing, the only thing I want to mention is if you're employing energy recovery, you always want to balance your system, always. But if you're looking at VAV, variable air volume, you want to make sure that your supply air tracks with your return air. If one is running off from the other, you're going to have significantly unbalanced flow and you have very, very unpredictable results. So make sure if you're using VAV with energy recovery, supply and exhaust track at the same, at the design proportion. Filtration and fouling. Filtration, when we talk about energy recovery, obviously adding a filter to your return airstream is going to increase pressure drop and increase your power consumption and your energy consumption. However, when we're talking about energy recovery, filtration is very important. In real estate, it's all about location, location, location. With energy recovery, it's all about filtration, filtration, filtration. Particularly if we're looking at enthalpic devices. An enthalpy device uses a very detailed or a very intricate pore structure to transfer latent energy. So in order to grab moisture from one airstream and leave that to another airstream, you want to make sure they're open. You don't need HEPA filters, but you do need some type of preliminary filtration in order to maintain that performance of your latent device. If you have a sensible device, if you have a plate or a heat pipe, you're much less subjected to the burdens of filtration. So depending on your application, if you have wastewater treatment plants or something that's a little bit dirty or something that you know is not going to be maintained ever, you may want to lean more towards some type of more robust, sensible device that's easier to clean and doesn't require as much filtration. But if you have a static plate, membrane plates, or if you have an enthalpy wheel, you do want to make sure you want to maintain a minimum upstream filtration. Anywhere, you don't need more than a load 8, but your minimum requirements for more filtration will more than exceed what you need to keep your device clean. If your latent performance ever drops off at some point, clean your device, and you will magically see your latent performance come back and change your filters. So, humidity control, I'm going to skip over that because I'm starting to get a little bit more time. Economizer, we talked about that before when we have the unbalanced airflow, or not the unbalanced airflow, but we're going from 10% to 100%. When you have that, how do you account for that in a design? You don't want to put 3 fans, you don't want a little fan, a big fan, and then another fan in return. Ultimately, the best way to do that is some type of barometric pressure relief in the exhaust air compartment, where you can allow that extra air to spill through, and then you size your device, your energy recovery device, for your minimum amount of outside air. So in this case, if I'm talking about 20,000 CFM and I have 10% outside air, don't size your device for 20,000 CFM. Size it for 10,000 CFM, draw through, in that particular case on the supply, and then allow for barometric spillage in your exhaust air, or you can do power exhaust in order to handle the extra air that's going to get pushed out back into the return. So it's a little bit more economical in that case. So ideal energy exchange, we talked about that. When you locate your energy recovery device, you want to remember 2 things. You want to maximize your temperature difference between the two airstreams. You're always located upstream of the mixing box. You always want to maximize the temperature difference. If I locate it downstream of the mixing box, I'm looking at 8063 versus 9578, and my return is 75. You want to maximize that performance. You want to maximize your moisture-driven humidity transfer as well. So you want to keep the maximum difference between the two. So you get that partial pressure-driven moisture transfer. You want to minimize your OACF as much as possible so you don't impact the overall energy costs. And you want to make sure you maintain the correct exhaust air transfer ratio for your application. If you only need if you have that 5 and 10% reclassification, design for the 5%. If you have 5%, let's say, well, I want to make sure I have 1%, you're adding a lot of extra outside air cost overall system. Make sure you're still going to be compliant, but make sure you're leading to that EATR. And again, you also have your standard conditions for any other project, which is going to be your budget and footprint and your other constraints that you want to see. So, applications, I'll skip over that because we're getting a little bit later. If you've never seen a heat pipe heat exchanger, I got about 5 minutes before my promised 45 minutes, but I don't want to cut you short. But you guys look, normally I'd give you a break right about now, you're pretty tired. But we'll just go over the exchangers and then we'll round it out real quick and maybe any questions that you have. So I'll make sure you get your money's worth, but my best rated presentations are typically the ones that finish on time. So I'm going to maintain that. If you've never seen a heat pipe heat exchanger, that's typically what it looks like. You're looking at an aluminum device. It looks very much like a core, a coil that you would see. However, it is not a coil. This is a coil. A coil has an inlet and outlet. A heat pipe has a bunch of different sealed tubes, vacuum sealed, charged, and individually located. They're not circuited together. Ultimately, the advantage is we have no moving parts. A lot of size flexibility for retrofit with respect to height and width, both in the supply and the return. You don't have to have a dead center for your center partition, which is right here. So my outside air, in this case, let's say would be going over here. My return air would be here. I have a center divider. Heat pipes used to be 80% of the overall market, if not more. Heat pipes are now probably about 2% of the overall market for energy recovery in North America. That 2% is primarily due to high pressure applications, dirty applications like wastewater treatment plants, wraparound for dehumidification type applications as well. But they are very, very good at what they do, and there's no other technology that can replace them for those particular applications to any effective degree. So we'll go over the closed loop evaporation and condensation cycle. Fixed plate heat exchangers, if you've never seen them, that's what the plate looks like. They can be aluminum, which is this little silver guy over here. They can be aluminum, or they can be polypropylene, which is the black and white one at the top, which is a fancy way of saying plastic. So both of those are also sensible devices. They only transfer temperature. Typically, you're going to be a smidge higher than your typical heat pipe for sensible performance, but they're also very durable. I should mention both of these devices, both of these technologies, also can handle high differential pressures. If you have an application with 10 inches of differential static pressure, these are the technologies that you want to go for. If you try to put 10 inches of differential static pressure onto a heat wheel, you're going to have unpredictable results. It's not going to perform as well in those conditions. These are very, very robust, a lot easier to clean, no moving parts, low maintenance. Very, very good. We see a lot of plates, also sub 10,000 CFM, sub 12,000 CFM, because again, you're dealing with a cube. Once you start to get larger, the limiting factor in this case becomes size. Your box becomes very much oversized, and competing technologies handle those larger sizes better. Having said that, I've done pools with aluminum plates or polypropylene plates up to 35 or 40,000 CFM. But again, it's the application that dictates the technology. I wouldn't normally suggest that for a standard application of 30,000 CFM because of the size constraints. Membrane plates are also very interesting technology as well. So you can get plates just like non-moving parts, but also transfer latent energy. They don't transfer as much latent energy as heat wheels, but you will still get about 50 to 60% latent performance of these devices. So pretty nice on that side of things. They've come up from the residential side of things a little bit, but they are becoming a lot more commercialized. There's a lot more manufacturers and become more cost effective. But the disadvantage of these devices is they also run slower than sensible plates. So whereas sensible plates, let's say at around 12 to 15,000 CFM, you're starting to question the overall size. Whereas those are designed at 500 feet per minute, these plates are designed typically at 250 feet per minute. So now you're looking at somewhere between 8 and 10,000, or maybe size is going to catch up to you before you can use them, which is why you don't see these everywhere else. Rotary heat exchangers is really the big one, the big application. We see it from the very, very small to the very, very large. It is a very, very flexible technology. There's a lot of different technologies. I could talk for an hour on the different types of constructions. But ultimately, you're going to have a different substrate, which is the basis. That's going to transfer sensible energy. That could be plastic, it could be ceramic, it could be aluminum. In the olden days, it used to be asbestos. Seriously, it used to be asbestos. Anyway. Then there's also the latent coating on the top that's actually going to transfer the moisture. You're going to have a variety of different latent coatings. You're going to have silica gels, which are very popular. You're going to have molecular sieves, and you're going to have ionic exchange. Ultimately, fundamentally, they all do the same type of thing. In the end product, regardless of the details, you're going to get relatively the same performance. Every manufacturer, they're going to rotate at different speeds. They're going to be different thicknesses, different sizes. The variations specific to your application are going to dictate your selection of components. If you have a seacoast environment that's very, very corrosive, you may want to lean away from the aluminum device, and you want to look at something that maybe has a plastic or a resin-based substrate that's not going to be susceptible to corrosion as much. If you have high differential pressures, you're going to want to lean away from, typically away from the wheels. Anything over 5 inches of differential pressure, I would look closely at what you're going to get for performance between that and lean towards another technology. But outside of that, they scale up really, really well. You can do, like I said, you can do 1,000 CFM and you can do 50,000 CFM. I've done applications, I've designed systems that are 100,000 CFM, 100% outside air with empathy wheels. Because they scale up really, really well, but they don't get much thicker, so your box is not insanely large. They also go at higher velocities, typically 700 to 900 feet per minute. So ultimately, that's why we see that, and it's also a very low pressure drop for the corresponding velocity and volume. So very compact at large volumetric flow rates, and that's why we see wheels just about in every other device. Very easy to implement as well. So you want to select the correct technology as we go through, without a doubt. And when we get back to the EATR and the OACF, we look at a nominal OACF of anywhere from 0.99 to a little bit over 1 for your heat pipe. In this case, we're going to look at sensible plates. You're going to look at a very similar range as well. But your EATR is going to be a nominal 0, up to about 5% for both of those devices. When I say nominal, nominal is what's going to be posted. But if you have a critical application, if you have an explosion-proof application, and you need true 0% cross-contamination, the recommendation at TC55 is to isolate those two airstreams and ultimately use a runaround loop if you want to use some form of energy recovery. Regardless of how you certify what the margin of error that you're allowed to claim for 0% is in any type of rating system, these systems also go into a box. If you have an airstream that is located side by side, you're going to have a center partition and then you'll get potential for leakage. So if you have a critical application, Ebola, explosions, anything like that, separate the airstreams. Don't look at energy recovery. That's all I'm saying. Or this type of energy recovery. So ultimately, I will round it out. We'll skip over the specification writing. In this case, but we look to HRI very much. Product sections, proper care and feeding, just want to round out to that as well. If you can avoid issues, some of the questions, some of the things that I brought up this afternoon, this evening, consider that. Ask those questions of your partners, particularly if you have a custom project, and make sure you look at your filtration. Always make sure, if you can specify it, make sure that you have proper access upstream and downstream in order to maintain the devices. Enough for a person to get in to be able to clean up the ones, and not just a 9-inch or 12-inch section underneath. The better you can maintain your product, the better it's going to perform overall. So that takes me around the bend. I guess I'll open it up to questions, unless you want me to talk. I have a lot more slides, but I'm going to let go.
Any questions for Paul?
Stunning.
All right.
Thank you very much.
A round of applause for Paul, please. Great, so that pretty much concludes what we're going to do here tonight. Thanks again to Paul for bringing this up. Obviously, you guys can tell that this is a more in-depth topic than we had time to get into tonight. Paul's presentation will be up on the ASHRAE website once we get it from him. But given our climate situation in Zone 7 and 8, you can see how important it is to consider this in your project. There's a lot of local representation for a variety of products to get the details that we need.
And if there's any questions, any technical questions, regardless of your affiliation, I'm more than willing to answer and help and push you in the right direction. Yeah, no, I'm here to help. Anything technical, feel free to contact me.
All right, so everyone who registered will be emailed a link to a survey which rates the presentations. These are really, really helpful for us guys to make sure that we get topics that you're going to enjoy and want to see for sessions and for years coming up. So please take 5 minutes of your day tomorrow and fill that out. I would like to give Paul this token of our appreciation. Thank him very much for his time. One more round of applause for Paul, please. So that wraps up tonight, and we are here next February 3rd Tuesday of the month. As usual, the topic is going to be our own Daryl Boyce giving us a presentation on the Snow Lab, so should be interesting. Keep an eye out for the communique as far as the details on that, and enjoy your evening. We'll see you all in a month's time. Thank you.
Oh, good day, sir. Yeah, and also that case zone, right? Oh, no. Yeah, because usually outdoor air. That case zone, right? The zone are right? The zone here, zone one. So they should let it go. There was more the odd right? Us becomes wet. What's the outdoor air percentage? You have your air temperature, right? Well, outdoor air, that's how much goes back into the so it's like 10% outdoor air. You have 90% working air going back.
Not this year, but